Okay, so today we are happy to have Vasilis Niarchos from University of Crete, who will tell us about conformal bootstrap versus reinforcement learning. So take it away.
Okay, thank you very much, Petra. So it's a great pleasure to be in this venue to talk about this subject. It's the best group to talk about the subject. I'm going to talk about some recent work that I've been doing with Kostis Papageorgakis in Queen Mary and his student Gergely Kantor, who's an excellent PhD student and has helped us a lot with the machine learning aspects of this project. Okay, so I don't think I need to motivate conformal field theory in this audience, so I will go straight to the problem. And so just to set up basically the context and the notation, let me say some introductory words. So I will be interested in conformal field theories in any dimension in flat spacetime. And as we know very well, conformal field theories compared to a generic quantum field theory is a little simpler to solve because at least the local structure of a conformal field theory can be characterized by a discrete set of data. So if you know the spectrum of conformal primaries, the scaling dimensions, the spin, or whatever other quantum numbers you have for the operators, and also you know the OPE coefficients, then you basically know the 2- and 3-point functions, and you can deduce all the endpoint functions of the theory in this way. Now, the nice thing, as you know very well, is that these data are not arbitrary, so there are several general constraints on them, like unitarity, crossing conditions, crossing constraints, etc. And by solving these consistency conditions, we end up with with a conformal bootstrap program. Okay, again, I don't want to do a review here, just to set up the notation. So if you give me a 4-point function, I can write it in 2 different channels. I can do the conformal block decompositions into different channels. And this is the general crossing symmetry equation that we have. And again, I write it down here just to set the notation. So I will be using this mathfrak sys to express OP squared coefficients. So this is one of the CFT data that we want to determine. And of course, we have this conformal block decomposition. We have operators with scaling dimensions delta running in the intermediate channel, and we can write the S channel expansion and the T channel expansion, and we have quantities, the conformal blocks that depend on the cross ratios like U and V in the standard way. So in what I will do, I will assume that we know explicitly the conformal blocks, and the name of the game is to try to solve these equations and find the C's and the deltas that can appear consistently in these equations. Okay, so clearly this is a difficult game to play, and the difficulty is obvious from the start. We have equations that are functional equations, and they involve here an infinite series, so many, an infinite number of terms. So we have an infinite set of equations for an infinite set of unknowns. Also, if we want to reduce this to algebraic equations, to algebraic constraints, then we have to reduce, if you want, this functional dependence on Z and Z bar, or U and V, into specific algebraic constraints. And this usually we do either by Taylor expanding around some point in the cross ratio space, or something which is less frequently done, but I will explore here, by evaluating numerically these equations at different points of U and V. And of course, if we want to actually solve fully a conformal field theory for any quadruple of conformal primaries, for all the 4-point functions, you have to simultaneously solve all these crossing conditions. So there are 2 general perspectives you can take here, either the one that has been very successful in the last decade, which has led to the modern conformal bootstrap, which you know very well, where you make some assumptions and then you try to eliminate them using unitarity as a crucial tool. And that is a wonderful tool. It gives you all sorts of rigorous bounds on several quantities, and has been very successful. Another perspective you can take is you can try to actively solve these crossing equations. This is more along the lines of the original bootstrap idea. But of course, without any assumptions, finding the general solution to these equations is not practical. So what I want to do in this talk is take the point of view, the second point of view, the less traveled road, if you want. And some of the reasons why we picked this approach, which we are going to attack with these machine learning techniques, is because I personally was more interested in the following kind of problem. So instead of finding some rigorous bounds on some low-lying CFT data, which is usually the kind of results that the first approach gives, but not only, it can give you more. But what I was more interested in was problems like this, where you give me your favorite conformal field theory, your favorite gauge conformal field theory, you know you know some things about this conformal field theory enough to basically guide the search towards that particular conformal field theory, and then you try to solve with these assumptions, you try to solve the constraint equations to compute quantities in that particular conformal field theory. So I don't want to make some blind assumption up front and then end somewhere. I want to start with studying a theory that I'm interested in. So what I'm going to try to do is try to develop a tool that can be guided with discrete assumptions towards a pre-selected CFT. So what do I mean by discrete assumptions? Basically what I call here a spin partition. In other words, when I write these sums here, I will make some assumption about what kind of operators, about the number of operators per spin that can appear in the sum, so that this set of equations gets converted into a specific set of algebraic equations, and it's not something very abstract. And also, once I make this assumption about, for spin 0, I have so many operators appearing, for spin 1, so many operators, etc. Then I want to have a tool that will allow me to do an efficient high-dimensional search in some not very narrow, but some rather wide windows in scaling dimension. So it's important for me not to have a tool that can only solve for low-lying CFT data, but that a tool that I can push to find, say, order 100 operators, etc. So the obvious issue I have to deal with here, I think it's obvious, it's fairly known, is that this approach, the second approach, which is not really new, is not going to be rigorous. So I'm not going to be able to derive rigorous bounds as in the first approach. There are going to be multiple sources of error, and I'm going to briefly discuss them. But as I said, my main concern here is not to have, at the first stage, it's not so much accuracy, but whether I can develop a tool that is a good discovery tool. So if this tool is not super accurate, but it can actually locate with some significant errors the theory I'm interested in, my hope is that this will be an interesting discovery tool that potentially can be used as a complement to the first approach, where potentially we can get much more accurate results. Okay, so here is a summary of the main steps I'm going to take when I try to solve. So the first step is to pick a 4-point function, which means give me 4 external operators with specific spins and global charges. In principle, the scaling dimensions of these external operators are unknowns, and I have to determine them. Then, in order to make these crossing equations specific and not so abstract, I'm going to truncate. I don't want to have an infinite number of unknowns, so I'm going to truncate the CFT data in the conformal block decompositions, and I'm going to use as an assumption a specific spin. I will call it a spin partition, what I mentioned before. That means, by definition, the spin partition is a prescription or an assumption that tells me how many operators I should expect in my truncation at spin 0, spin 1, spin 2, whatever, within a specific window of search. So I'm not going to be searching for scaling dimensions from the, from the unitarity bound up to infinity. That's not going to be very practical, but I want some large window and, I expect so many operators in that particular window. So that reduces the number of unknowns, or if you want, it reduces the dimensionality of the search, to a specific number. So I will have n unknown parameters. So half of them are going to be the scaling dimensions, and half of them the corresponding OP squared coefficients, which I can arrange into vectors. Okay, so this is the space of unknown parameters. Then I need to reduce the functional ZZ bar dependence, and I can do it in different ways. So the most common way is to do Taylor expansion or to do a Z sampling. In other words, evaluate these crossing equations at different values of the crossing ratio space at values of Z. We're going to follow the second approach here. This has not been explored very much. There has been a paper in 2016 that was exploring different Z samplings, and we're going to mostly using what I will present. We're using the Z sampling that was favored in that paper. In any case, what I'm going to do here is I'm going to reduce these functional equations to NZ crossing equations, algebraic equations, and I want the system to be overdetermined. So I want NZ to be greater than N unknown. And now we come to the final and a fourth step. Now, once we have this overdetermined system of equations, we do not expect in general to have an exact solution of these equations. So the idea here is to take that vector of equations, which is NZ dimensional and depends on N unknown coefficients, and we want to minimize for each component the violation of these equations. So the way we're going to do it is we're going to choose a particular, if you want, norm in this vector. So we can take the most obvious choice is to take the Euclidean norm and try to find the profile of deltas and C's that minimizes this quantity. Obviously, this quantity is not a unique quantity that we can choose. And later on, we can discuss, whether it will be interesting at a later stage to explore different definitions of E that maybe can facilitate better searches. Okay, so obviously this approach here so far is not new. I think the first who proposed a similar approach was Gliozzi in 2013. He did essentially the same thing. He took these crossing equations, he truncated them. And one major difference with what I'm going to discuss here is that he truncated the equations and treated them as exact equations, although he still had an over-constrained system of equations, so viewed as a system of linear equations for the OPE squared coefficients. Okay, he wanted to get actual solutions for these equations. Obviously, this is not going to work always, but in case sometimes it works. And by setting to zero the subdeterminants, he was able to get the data for the low-lying scaling dimensions. In 2017, this was reformulated as an optimization problem by Wenliang Li. And basically what he proposed in that paper in 2017 is exactly the same kind of thing that I will be doing here as well. So he introduced this norm of E, and he proposed that we should try to minimize this. And the idea is, of course, that as we include more and more operators, that E minimum, the minimum value of this quantity will try to go towards zero. And then you're converging to an actual solution of the crossing symmetry equations. Now, one difference with this approach is, as far as I understand, at least by reading these papers, is that the main focus in these early approaches was that it was a nice tool, a convenient tool that is easy to more or less to implement. It also applies to non-unitary theories. And the idea was that we would use this tool to get information about the low-lying spectrum. Here, we're not interested just in the low-lying spectrum for several reasons. We want to push a high-dimensional search and get as many operators into this game as possible. One reason is because we're interested in applications where we would like to know about lots of safety data. And the second reason is because we want to understand better the errors that come into this approach. And in order to probe, for example, the errors that come from the truncation, you want to put more and more operators and see if the approach, if the results converge. But in order to do that, you need to be able to go high in the scaling dimension, the cutoff. Okay, so I already mentioned some of the uncertainties or errors that appear here. The first 2 points here, the error sourced by the truncation and the error sourced by the reduction are obvious, I think. Let me mention here that, okay, first of all, it's not so easy to probe these errors, and there's not a very good understanding of the analytic understanding of these errors. And I think this is a deficiency of this particular approach. Presumably by having a tool that can do high dimensional searches, maybe we can gain a better understanding in 1 and 2. In any case, this requires further work, and I think it will be nice also to do some related analytic work that will try to constrain more the errors that come from 1 and 2. There is another source of error in what I will do next. The way I'm going to try to solve this minimization problem is not going to be the standard numerical approach, but it's a gradient descent method or something like this. I'm going to use a probabilistic approach, and that means that every time I do a run, I get slightly different numbers. So there's also a source of statistical errors here. And in order to get a feeling for the statistical errors, you have to do lots of multiple runs. And the only way you can do this efficiently is if you can parallelize the code. So in the results that I'm going to present, there are only a few cases where I will show you statistical errors like this. And since the publication, since the posting of the paper, we have been able to improve several aspects of the code. Now it runs faster, and it is more automated. In the future, it will become even more automated. And we believe that making it parallelizable is feasible. So we think that this third source of error can be addressed. Now, so the reason I'm mentioning these errors is because of 2 reasons. The first is the actual physical problem, right? We're doing these truncations because we actually want to get an approximation to the exact analytic result, and we want to know when we do a numerical calculation how far we are from the exact analytic result. Another reason, which is more practical and will play a more direct role in what I will discuss here, is the following. So when I do a run with the method that I will, with the algorithm that I will show you, the code starts running, and in principle, it will convert to an answer in infinite time. So obviously, I don't have infinite time to wait. So at some point, I have to stop it. And it would be nice to know if I am close to the expected value, the expected minimum value. So if I know that I'm close to the expected minimum value, I can just stop it. However, this minimum value is some unknown functional, if you want, of the truncation and the reduction that you're doing, or the specifics of the correlation function. So in general, you don't know where you should stop. So that's a practical question. When should I stop the run? In other words, if I give you a value of phi, if I terminate the run at some intermediate point, how do I know that this value is small or large? So if you look at the crossing equations, there are some positive terms there and some negative terms there, and they almost cancel each other. So if I'm canceling, say, 999 out of 1,000, so a difference of 1. The difference of 1 in 1,000 is a relatively small number. But if I have a cancellation of the order of 2 minus 1, then this is not a significant cancellation. So in order to get a heuristic feeling, a heuristic measure of, if you want a percent measure of the violation, we define this quantity here, A, which is called the relative measure of accuracy. It's not used actively in the running per se. So the algorithm always tries to minimize E, but we also record this value to have a sense of, as a percent error of the violation, how far is the violation compared to, say, the sum of the individual terms that appear in the crossing equations. So you see here I have E in the numerator and what I call E absolute in the denominator, which is simply take all the terms that appear in the crossing equations, absolute them, and sum over all of them and sum over all the crossing equations. So by the triangle inequality, this is going to be a less or equal than 1 number. So simply, we did several runs in different examples, in different theories, and empirically we noticed that we always get the solution below 1,000. So if, for example, you do a run and you see that it saturates, let's say 5%, at least this is some preliminary indication that maybe you're not going to get a solution. You should reject these kinds of profiles, or you should continue running it. So that was one empirical rule that we used for when to stop the run. And also we kept it running until we saw a clear saturation of E. So we had to see that E stops improving, and then for sufficient amount of time, and then we stopped it. Okay, and this is how we recorded the results that I will show you in a moment. Okay, before I go on, let me make a disclaimer. In what I will present, the results I'm going to present here were mostly meant as preliminary efforts to calibrate the algorithm. So basically, we had an algorithm in mind of using an algorithm that will solve this minimization problem. And we wanted to see if that algorithm works. So there's a problem of, you do this minimization, how does it compare to the exact analytic solution? There is another problem where you just focus on the truncated reduced crossing equations, and you ask, how well does the algorithm work for this particular equations? So we're only going to deal with the second problem. So that means that we did not make a serious effort to go for accuracy or to perform a systematic error analysis, although in some examples I will show you at least the statistical errors. Okay, so our main concern was to basically answer the following preliminary questions. Does the algorithm work? And that means for us, does it minimize this norm? Is it a promising tool? Can it work in cases where other non-numerical algorithms do not work as well? They take a long time, or they get trapped in local minima, etc. So that comes to the second question: how does it perform in high-dimensional searches? How many operators can we include? Also, if we look at different theories, is it easy in one theory, difficult in another? How does the algorithm behave in different cases? And also very important for us, can it identify known CFTs? So for example, if I give you a theory, the spin partition of a particular theory, will the algorithm, just by knowing the spin partition, the rough structure of the spectrum, will it be able to identify the CFT of interest? Is it a good discovery tool? Okay, so here is the algorithm. Okay, so the idea was the following. Since we're interested in doing high-dimensional searches, in other words, dealing with lots of data, what came to mind was all these recent successes of machine learning algorithms in this context. So machine learning is all around us. It is being applied in more and more contexts, in real life, in all sorts of scientific problems. I just want to mention the three main flavors of machine learning here for those that are not experts. The first, because all of them appear in, for example, in applications in string theory, applications or in other scientific problems, all of them appear. And it's only one of them that we're going to use in our approach. So the first one is the so-called supervised machine learning algorithms, where you have a bunch of data, you take a subset of this data, which you use as external input, and then you use them to train a neural network. So you can think of the neural network, if you don't know what it is, as a universal function approximator. So it has lots and lots of parameters, and then you use this external data to fit these parameters, and then you use this neural network to make predictions. So usually this is used to, I don't know, recognize patterns and do regression, etc. There's another flavor of machine learning, so-called unsupervised. Here, you don't need any external input. You don't need to supply external data. You don't need to train it. It goes through a large data set, and these are algorithms that are designed to recognize structure in these large data sets. And then there's a third flavor of machine learning, which is more, more intelligent. In this one, there is again no external input. Here you have to play a game where the rules are known. For example, you have to solve an equation or actually play a game like play chess or Go, whatever. And the brain of the algorithm, what people call the agent, learns by experience, by trying again and again, making efforts, and every time learns how to achieve these rules. So in our case, for example, where we have to minimize something or solve some equation, that looks like an appropriate tool to apply, and that's what we tried. So reinforcement learning has been used to beat video games, drive cars, guide robots, etc. And one famous example from 2016, 2017 is DeepMind's AlphaGo and AlphaGo Zero, where reinforcement learning algorithms were used to beat the Go's professional champions, and that was in the news. Okay, so here is a very schematic picture of how these kinds of algorithms work. So as I told you, there is one component is the agent, the brain of the algorithm, and the other component is the environment. The environment is basically the set of rules. So the agent starts in the beginning, essentially randomly, and makes, so for us, the environment contains the parameter space and also, knows about the reward, etc., the cost function, this norm E. So we have the brain, the agent. It makes a random choice in the beginning. It takes an action, and then it communicates with the environment. It gets some feedback from the environment. What is this feedback? One feedback is the reward. So the goal of the agent is to get the maximum satisfaction, the maximum reward. And when it makes an action in the beginning randomly, it communicates with the environment, gets some answer, some feedback. You made a good action or you made a bad action. At the same time, there is a multidimensional array that records the experience of the agent. Basically, it keeps a record of the actions that have been taken. This is the memory buffer. At the next step, which is basically the heart of the whole algorithm, this part of this memory buffer, part of this experience is being used to update the policy. So this is the learning part of the algorithm. So basically here there are neural networks inside this part that are not used to make predictions for the actions. They are not used to predict values of the safety data in our context. What they are doing is they are trying to approximate certain functions that will predict the probabilities of making a good action, for example. And these are fixed networks. So you may have a problem with 10 operators or 1,000 operators, and these neural networks have the same fixed size. Okay, so they scale well. So it's part of why this may scale well when we increase the number of operators. So we use this part of this experience here to train these neural networks and update the policy. Once the policy has been updated, it feeds back to the agent, and the agent makes another action. Now better informed about which are the most, which actions have the largest probability to be better. Okay, so, and this gets repeated. So this is like, this is not unlike a human, for example, where, when you're in a new environment, you learn. How do you learn? You take actions, you learn from your mistakes, and then you make better actions. And that's how this thing works. Now, another thing that another nice feature of these algorithms is that they have nice capacities on exploring the global structure of the parameter space, because they have this probabilistic, they work probabilistically, so they jump around, and part of them wants to get a better reward. And there's another part of it, another part of the algorithm that wants to explore. Sometimes the algorithm makes a bad choice, okay, just to gain experience, to see what's out there. So now all these algorithms have been developing for all sorts of different purposes. And now they are at the stage where basically you can use off-the-shelf algorithms or codes to implement basically anything you want. So we were interested in an algorithm that has nice features in terms of exploration and can also deal with continuous parameters. And one of these algorithms is the SoftAct Critical algorithm that by Harnouja, Zhu, Abil, and Levin that was developed in 2018. It was originally developed for a completely different problem. They were interested in robotics. If you look at their paper, all the applications are about robots and how they interact with their environment. But it's exactly the same kind of algorithm that we can take and apply in our context with these truncated, reduced crossing symmetry equations. And in our case, the reward is going to be minus E. I put the minus sign here because, the algorithm naturally wants to get better and better, larger and larger reward. And that happens when E becomes smaller and smaller. Okay, so what are the expected advantages of these algorithms? We expect them to have better scaling properties as you increase the dimension of the search, and also not to get stuck so easily in local minima. So to explore the global structure of the parameter space. And this is what we hope we will be able to gain from this. Now, before I go on to specific applications, here are a few more details about how we run the code. As I told you, the basic assumption here is the spin partition, how many operators you should expect per spin, and then you get a specific set of equations. So what I will call mode 1 is if you want the fully exploratory mode, where I give you the spin partition, I give you rather wide search windows for all the safety data, and then I let it run and see if it can locate a potential minimum. Mode 2 is semi-exploratory. So I give you the spin partition, but say that I have information about some of the safety data. Then I use narrow search windows for this subset of safety data and wider windows for the remaining safety data. For example, maybe I have some idea about where I should be looking for the scaling dimensions. So I use narrow windows for the scaling dimensions, but I don't know a lot of things about the OPE square coefficients. So I use larger windows there. So that will be a mode 2 type run. And mode 3 is a narrow search where basically I know my solution, the roundabouts of where I should be expecting all the safety data. And then I'm performing narrow searches and I try to see if everything gets stabilized in the region that I'm interested in. So this potentially could be of interest. So suppose that you have a theory, it depends, say, on a conformal manifold. It depends on some exactly marginal couplings. There is a weakly coupled corner of this theory. At this weakly coupled corner, I can solve the theory, I know the spectrum, I know where I should expect my CFT data. And then I start adiabatically changing the exactly marginal coupling. And as I change it adiabatically, I'm doing this mode 3 narrow search every time, trying to track how this data change as I change slowly the exactly marginal coupling. So this could be a large expansion or whatever. Okay, there is also another way you can use mode 2 and mode 3, which is the following. And I think this is an interesting aspect of this application. So we call this the incremental mode 1. So suppose that I use the fully exploratory mode for a few low-lying data that fix the kind of CST that I want to determine. So suppose that I have, I don't know, I want the 2D Ising model, simple case. And I take a few low-lying operators, I solve the low-lying, for the low-lying data with a mode 1 search, which has considerably large search window. So I really discover the solution. And then you can say, okay, maybe I don't have lots of information for the spin partitions at higher cutoff. Can I discover it dynamically? So one thing you can do, and this is actually some of the data that I will present, we're running this way. You take the low-lying data, you get the solution for the low-lying data, you add one more operator, say at one specific spin, you run the code to see where it wants to put, you fix, you do a mode 2 run where you fix the low-lying data and you let the new operator go wherever it wants. It stabilizes somewhere, then you let everything run together. And now you have a solution with a slightly enlarged spin partition. Then you can go on incrementally to add more and more operators in this way. So this is I find this particularly interesting because you can start by discovering a low-lying data and then gradually start building on top of that. Okay, so let me now, for the hour that remains, let me give you some examples of some runs that we did. So originally we said, okay, we should first try to calibrate this in some theories where we also know the exact analytic solution, just to see if it works. It wasn't at all obvious to me, for example, from beginning that if I give it, say, the 2DS1 theory and give it a spin partition, that it will actually be able, just from the spin partition, that will actually work and locate the theory as it should. So, okay, we said, what is the context where we know lots of data, where we know lots of exact analytic solutions, two dimensions. We also know also all the spinning conformal blocks there in analytic form. There's a nice paper by Hugh Osborne, who I think first got the general expressions for this. And so we have all this, this is a perfect place where you can calibrate. On the other hand, we don't want to use special features of two dimensions. So we don't want to use the Virasoro symmetry. And so we're only going to use quasi-primary. So only the global part of the conformal group. So the notation I'm going to be using is the standard one. So for the scaling dimensions, I will write them as the sum of the left moving and right moving conformal weights. The spin is the difference. The conformal blocks are explicitly known in terms of hypergeometric functions. I will call them G, and sometimes you will see the notation G tilde, where I have combined the contribution of H bar and H bar H, okay, where this is appropriate. Okay, so here again, rephrased in two dimensions, the steps I have to take. You give me a 4-point function. I write down the crossing symmetry equations. I truncate using a spin partition. I reduce with a grid of Z points. Okay, again, we could also explore the possibility of doing Taylor expansions. In what I will present, we did Z sampling. The Z sampling that we're doing is basically a uniform Z sampling. So we're picking in 1/4 of a disk, we're picking uniformly Z points. And then the problem we have to solve, once we have this truncated, reduced set of equations, we build this, we compute the norm of the violation of E. And we want to minimize that to find scaling dimensions and OP squared coefficients. Okay, so in principle, we can also vary we should also vary the scaling dimensions of the external operators, because in general, they're not known. Okay, so here's the first, if you want, baseline example, the minimal model in 2 dimensions. We have 2 non-trivial conformal primaries here, the spin and the energy density with the well-known OPs. We also worked out, that's not very difficult, we also worked out the quasi-primaries. And say we want to do this 4-point function, sigma, 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 sigma. We have this spin partition. So secretly, behind the agent, we pick some, we make a truncation at some delta max. Here it was 6.5. That instructs us to pick 5 operators in total. That's spin 0, 2, 4, and 6. We used 29 crossing, so 29 instances of the crossing symmetry equations. We evaluated them on 29 different Z points. These are the crossing equations. And then we did the minimization. And you can see that the results are not so bad, especially for operators that are not very close to the upper cutoff. We get pretty decent results. Again, it's not very appropriate to compare here directly the results that I get with the analytic results, because at this point, I don't know how far away I should be from the analytic result. Plus, I should be giving you here at least statistical errors. So I will present some examples of statistical errors later on. But from this single run, I want you to see that the code works. I can see that the code works because, you know, it gives me this relative measure of accuracy, which is 10 to the minus 6. It has really brought down the error a lot, and then it saturates at this value. In this particular example, we could also use delta sigma as an unknown and extremized also on that. Just for convenience, we didn't do that. We fixed it at 1/8. Also, as a measure of comparison, if you take the exact analytic results, plug them into the truncated reduced crossing symmetry equations and evaluate the norm of E, it's typically 2 orders of magnitude larger than the one that the code has found for its profile. So that means that the exact analytic result for these truncated equations is not a very good profile. Whereas the profile that is being discovered by the algorithm is a much better one. This was done with a mode 2 run, again, just for calibration reasons. So we started with narrow search windows around the deltas, and you know, from 0 up to whatever, I don't remember now, but with some sufficiently large window for the OPE squared coefficients. And you know, initially the code explored, you can see the C's running away and then eventually converging to these profiles here. Now, if you see how much time it took, this was run on a standard laptop, and it took around 12 hours. That sounds a lot, like a lot. Now, the reason why it took so much time, and we discovered it later, is because of how the particular code that we wrote, the particular Python package that we used, evaluates the hypergeometric functions. So now we have tried different Python packages that can reduce this 12 hours down to 30 minutes, which will be a significant time improvement. So the point is that in future versions of the code, this time here will also be considerably improved.
Can I ask a
Yes,
question?
yes, please.
What is the precision at which the calculation is run, at which the minimization is run?
So here it's a single run. So later on, I will tell you, when I do multiple runs, you will see what is the standard deviation from all the runs. And that's the only error I can quote at this point. And the other error that I can quote is, you know, what is the violation? What is this quantity here? Oops. Where is it? Here, this quantity, this Euclidean norm. So if you ask me what is the accuracy or error compared to the exact analytic result, I don't know that. And I haven't tried to probe that because I haven't made a serious effort to say increase the number of operators here or change the z-sampling and see how things move around. In principle, we want to do this, as I will mention later. This is very high on our list, but here we just wanted to see if this algorithm can do the minimization. Have I answered the question?
No, actually, I'm asking a more basic question.
Oh, okay.
So here, like the
you're asking numerically how many digits?
Error is minimized to 10 power minus 6. So what is equivalent to 0 in this algorithm, in this run?
I think we're working at I don't know, 7 to 10 digits, something like this.
Okay. So it's pretty close to machine precision.
Yeah, exactly.
I have another question.
It also depends. Yes, I'm coming. It also depends on the Python packages that we're using. We're trying to play with different Python packages. Yeah, please go ahead.
Just this is a very basic, but the narrow window, like in terms of the relative to the dimension of the operators, how narrow is it?
So I will take, say, something like 0.5, 0.2, but then it can start moving. So I start with a window. So I didn't mention this. I removed this slide. So in the code, we have, actually, this is a good opportunity to mention this. So the way we've written the code right now, you're given 2 dials. You're given the floor of the, say, the scaling dimension or any safety datum. So the minimum value where it should, you know, and some maximum if you want, or the size of the window. So it starts probing inside there. So it starts probing, this can start moving around. Okay. So when I say narrow windows, I mean we started here with, say, close to the analytic values, plus or minus 0.5, say something like this.
Okay, thanks.
Okay. Now, this is not done because this is the best we could do. You could do larger windows. In general, in the mode 1, we did larger windows. But here we wanted to push it close to the, you know, it was sort of lazy here. Very simple theory. We're not very interested in this theory. Let's push it very close, rather close to the analytic solution, at least for the scaling dimensions, and see if it minimizes. So this is the only thing I'm showing here. I'm not making a serious effort to be very exploratory or whatever, or to push the boundaries of how large the windows are. I can, you know.
Thanks.
Okay, thank you. Then we tried the criticalizing model. It's a little more interesting. It's a more interesting theory, as you will see in a moment. It has more operators, but also some of the OPEs here are very, you know, are exactly the same as the ones in the Ising model. And we wanted to see if the code suitably guided can differentiate between the two theories. So, for example, if you try the sigma prime, sigma prime, sigma prime, sigma prime, we give it a slightly different now spin partition. Now, this is a 14-dimensional set, which means we have 7 operators, but it's a 14-dimensional because we're also varying in the OPE squared coefficients. Again, for convenience here, we fixed the external scaling dimensions. Again, I do 5 operators or 7 operators here. Again, just as a simple illustration, we will go much higher on the scaling dimensions. In the next example, which is more interesting, I would do how many? 18 operators. And even there, we could also go higher. Okay, so you do this spin partition, you write down the spin partition. This is the sigma prime 4 times. Again, it's especially for the low-lying operators, it's not so bad compared to the analytic results. And again, the comparison with the analytic results is mostly heuristic to see if we have identified the right theory. So for example, when we first ran this, did this runs, we hadn't even computed this analytic values of C. So we're running very blind. And it was very satisfying when we computed them to see that we were not falling very far away from them. Again, this was again a mode to run where, you know, this was not the windows here were not very large, and but you know, it was exploring quite a bit on the OPE squared coefficients. Also, if you compare the energy density 4-point function in Ising and the energy density epsilon double prime in the criticalizing, the OPEs are the same. So in the intermediate channel, you're only running quasi-primaries in the Virasoro family of the identity. So you have this, basically for both of these 4-point functions, you have the same spin partition and just different external scaling dimensions. So there are some interesting games you can play here. You can leave the external scaling dimension as one unknown and try to vary the whole thing. I will present an example like this later on. Here in these runs, we fixed it at 1 and 3 and try to see if it will locate the theory. The run was pretty simple here. Again, in all of these examples, you see that A goes down significantly. The result compares quite favorably, let's say, with the first stage with the analytic results. One interesting thing to notice here is that this theory, the structure of this theory makes the search much more challenging, much more complicated. So one thing, and you notice here that here I quote a single run for the Ising, which has 5 operators, and here is another run with 8 operators for the criticalizing. There's also a run with 5 operators where you can directly compare these two, and you will see that the criticalizing was much harder. The numbers, also some numbers do not come out, at least in the single run, very nicely. And that's why I present here an example with more operators. You see that it worked quite well, but this was a mode 3 run, which means that I started rather close to the analytic solution. Then I let everything run and stabilize somewhere. Now, what makes this example much harder than this example is the fact you can already see the OPE square coefficients here range from 0 to 40 or 42 or something, whereas here they range from 0 to 1. Okay, so if I really wanted to do here a full exploratory run, it would have been much harder because I have to open the windows a lot, which makes it rather challenging. So it will be interesting in the future to try to push this, to see how large windows can we accommodate. Play a little bit more with examples like this. That's all I'm trying to say.
I have a question regarding the OP coefficients, because in the case where you have just one crossing equations, it's relatively easy to see that the OP coefficients are quadratic. I mean, the crossing equations are quadratic in the OP coefficients. So you could actually minimize with respect to them analytically.
Yes.
I mean, it can also be done for more correlators, but in this case, it's relatively straightforward. So was there a technical problem or something that did it work better like this?
No. Well, obviously, if you have a few operators, I think the way you propose is going to, with standard numerical techniques, is going to work much better. I think it will. However, if you start including more and more and more operators, and you try to minimize that square root of sum of squares, right, for the crossing equations, where you vary both for the scaling dimensions that are highly nonlinear and this OP square coefficients, that's going to be a harder problem. Am I answering the question?
I'm not sure. So
if you fix the scaling dimensions and try to minimize for the cis only, then it's much easier. That's what I'm trying to say.
No, but I'm saying, but
if
for
you try to minimize everything, and you have lots of operators, it's not going to be very, very easy.
No, but at each step, one could consider, for example, that your reward function is that the learning algorithm is just trying to give a prediction for the deltas, because given a set of deltas, you can calculate the OP coefficients by minimizing these least squares.
You're trying to see if one could do a hybrid.
Yes, like
yeah. We haven't tried that. That's a good point. Yeah, one could try things like this. I don't know how fast it will be, however, because it will have to do the steps. One step. Like it will have to do combination of these two things, and the question is how costly it will be, time-wise.
Yes, I have no idea of the internals of the prediction.
No, but this could be one could try that.
Can I ask a question about these results?
Yes.
Is the claim that once you fix your windows, you uniquely land on the known theory?
That's the hope, and that's the thing we wanted to test. You would expect that, if you sort of give the right windows and the right number of operators, probably you will land in a known theory, but that's not so obvious, right? The code will try to dynamically, as we will see later on, will try to turn off an operator, or you're not giving this. I don't know. You could also give these operators in a rather random way, so not with a fixed maximum for all of them. So it's not completely clear to me that giving the spin partitions will necessarily land you in the theory that you want, but it certainly guides the algorithm towards not a lot of choices, right?
So in the cases you checked, for example, 2D
in the cases we checked, it goes here. It's not very interesting because if I'm running mode 2 or mode 3, it's not very exploratory. So I'm pushing it. The windows are sufficiently small that it's pushed there in any case. The next example that I will show, we use larger windows and only the spin partition. It was a nice surprise to us that it actually landed to the theory we wanted to land.
Okay, thank you.
Okay.
So I also want to know whether you require the operators to be unique and not degenerate.
Yes, good question. There was a slide that was this comment here. So if they are degenerate, obviously the c-squared that we are computing is the combined c-squared. Okay, because these equations can only see the combined c-squared. So they cannot tell you if there is a degeneracy or not. So if there are two degenerate operators in the spin partition, we put one.
In this, specifically in this example, if you expect there to be 5 operators, and if 2 are degenerate, they will,
Yes.
the reinforcement learning will only see 4.
Yes.
So what happens to the 5th operator, which is clearly above delta max?
Well, one thing that will happen, you have to see case by case what happens. One thing that will happen is tries to push you away from the, so you put a window and you can see it actually trying it goes towards the boundary of the window and tries to go away.
Okay.
So you can see this.
So you have access to all of these.
Yes, it could also turn it off. It could also turn the C squared of that operator to 0 and effectively eliminate that operator.
Right. Yeah.
Okay.
Makes sense. Mm-hmm.
So now you will see something interesting that happens in the next example, and hopefully I can finish in 4 minutes. Okay, so the second, this was the most interesting example, I think. So let's take the point of view of the agent that doesn't know a lot. So I will try to present it like this. So we asked the agent to identify a 2D CFT that has a U1 global symmetry. It has an exactly marginal deformation, and it has a scalar charged operator, OP. We could have used also spinning operators, but we use the scalar charged operator that we labeled by some linear number P. So this P here is just square root of delta of this operator. And we're using the scaling dimension of this operator as a proxy for the conformal manifold coordinate. Okay, so the idea is that since we have an exactly marginal operator, we assume that we can use a scaling dimension that this scaling dimension depends on where we are the exactly marginal coupling, and we can use the scaling dimension to fix the point on the conformal manifold. And we also wrote down this 4-point function, O bar, O bar. Okay, and then we provided the spin partition. Now, secretly, we know what theory we want to reproduce. So this is not a random spin partition, but the agent doesn't know that. First, we gave it, we did it in steps here. So we wanted to see how things change as we increase the cutoff in the scaling dimension. So this is the spin partition for 2, 3.5, 4.5, 5.5. But basically, we could also have not provided this 3.5, 4.5, and 5.5. We could just give you the delta max equals 2, and then incrementally start adding one more operator every time and try to dynamically reconstruct these spin partitions. Anyway, so we give the spin partitions, and we try to solve these crossing equations. This is used as a proxy. We used it, for specific value, we took delta p equals 0.1. And so here are the results in the S channel and the T channel. So you can see here, we see in the T channel, in the spin 0, we can see an operator with scaling dimension 2 that sounds like the exactly marginal operator. Here we see an operator with almost 1 scaling dimension that sounds like the current, the U1 current. And we also see a spin 2 operator that has almost scaling dimension 2 that could be the energy momentum tensor. And again, the point here is that we minimize A. And in this example, we also did a statistical run. So we ran it 12 times. You can also see errors here. So in future, if you want publications or results that we will obtain, you will always see such errors. So they will not be single run, single values. And that gives you a nicer idea of, where the values, where does the algorithm statistically land. This is for 3.5. Notice also here, we have the same operators, OP, OP. So in the S channel, I shouldn't have any odd spin operators. So to confuse the operator, we gave it also in the spin partition, one operator of odd spin. And the algorithm sensibly tried to eliminate this one. So it gives you an OP square coefficient that is 10 to the minus 7. Okay. Okay, so 4.5 more operators. 5.5 was the higher we tried. We could go higher. This is 18 operators. We could go higher. Here I say 4 days because these are 2 runs. So each run, I ran the thing independently twice. So each run took about 2 days, but now with a better evaluation of the hypergeometric functions, this could go, I don't know, to a couple of hours. So it can be drastically reduced in time. Okay, so one feature that I want you to see, don't want to take too much more time, just a couple of minutes. One feature that I want you to see is this red circle. You see the low-lying scalar operator, 0.39, 41, 40. It goes towards 0.4, which is 4 times p squared. So in other words, this OS seems to have a scaling dimension, which is like 2p squared. So since the U1R charge is an additive quantity, it seems like this label P here, which was square root of delta, looks like something proportional to the U1R charge, to the U1 charge. And we also vary delta P on the conformal manifold, and we get the same result. So basically there is a slope here, which is close to 3.99. So that fits very well with what we were trying to, the corner we were trying to push the algorithm. We were trying to push it to discover the 2DS1 CFT. And this picture that I just shown you fits with the interpretation of this OP as, since it's a scalar operator, it's either an operator with momentum or winding. Again, if you know that this is the theory, you can write down the quasi-primaries. Now I can add in this list also the analytic results. And you see that we're not very far away. Let me go here. Let me make some comments. First comment here is that when we do this runs, we are not using unitarity. So there are minus signs and plus signs here in the OP squared coefficients in the T channel. And we let the algorithm run with, it could explore both pluses and minuses. And in the T channel, it found the right signs, which is encouraging. It made a mistake here in the small number in the S channel. Okay, and here is the largest scaling dimension. One thing, several comments here, which I think are important takeaway lessons. First of all, if you notice all this, if you look closely now, I sort of ran through them, but if you go in the paper and see how the numbers compare for each cutoff as I increase the cutoff, you will see that they systematically improve with as I increase delta max, which is a good sign. So it's a sign of convergence for the scaling dimensions. Also notice something else. I have 3 operators here without spin. They are not supposed to be there. So the code is trying to turn them off with 10 to the minus 4, 10 to the minus 5, 10 to the minus 5. But the surprising thing to me was that it was so if it's turning off these operators, the scaling dimension shouldn't matter too much. But it's actually predicting values for scaling dimensions of operators without spin that exist in the spectrum of the theory, but are not supposed to be in this conformal block decomposition. So just by putting a wrong operator that shouldn't be there, the algorithm, first of all, tries to turn it off. And secondly, it also says something about the scaling dimension of this operator, which doesn't seem to be away from the expected analytic value. I was also worried the systematic improvement here was not so evident in the OP squared coefficients, and I was pretty worried about that. Maybe it was the sampling, maybe I wasn't running the code very, as much time as it should. But then if you take the scaling dimensions and take these crossing equations, and instead of doing a Z sampling, you Taylor expand around, say, the UV crossing symmetric point, then you have a linear system of equations. Say we have 18 operators. Let's write down, let's do the Taylor expansion around U equals V equals 1 and keep 18 equations. Then it's a linear system for the OP squared coefficients. What values do we get? And you get very much comparable values to what the algorithm found. So you can see here, there are some huge discrepancies of 4 orders close to the cutoff. And this Taylor expansion is also reproducing that particular discrepancy. So that means that the code is working, but there is something analytic about the Z sampling, the Taylor expansion, something analytic to understand better here. Okay, and finally, we also did the 4-point function of the current, very simple spin partition. And here we also varied the scaling dimension of the current, and it found it very nicely, very close to 1. Here, there are also statistical errors, etc. Okay, so I can stop now. I think I went 5 minutes or 2-3 minutes over time. Very quick comments, we try to explore here. So this is very preliminary. We try to explore if these reinforcement learning algorithms can perform high dimensional searches and whether they can be guided to identify desired CFTs. I think the first results are encouraging, and I think they are worth exploring further. In future versions of the code, you should expect faster, more automated algorithms that can be parallelized. That means more accuracy, more operators. And my personal hope here is that maybe this will not be maybe this will not be a tool that gives you the rigor and accuracy that other methods like the unitary conformal bootstrap is giving, but maybe this is a good exploratory tool that we can use as a complement to the efforts that other people are doing with other methods. Okay, we need to improve the error analysis. It will also be interesting to explore other algorithms or other variants. Some people suggested other variants of these kinds of runnings. And we're very eager to go beyond the calibration stage and start applying this to more interesting CFTs, 3 dimensions, 4 dimensions, 6 dimensions, with or without supersymmetry. So hopefully, not in the distant future, we will be able to report new discoveries. Thank you very much for your attention.
Okay, thank you, Vasilis. Let's thank the speaker as far as it's possible. And yeah, are there any questions?
So I would like to start with an almost philosophical question if nobody has anything more pressing. So maybe you say that the reinforcement learning, the algorithm that you use trains the probability distribution that it uses to then sample the conformal data.
Yeah.
Is this built into the algorithm, or like it would seem? I don't know. It seems like a very, at least to me, very unnatural thing to do in the middle. If you're interested, why generate the probability distribution instead of just
okay.
training?
Yes, first of all, I am a complete novice in these algorithms, and I'm also learning about reinforcement learning. So in this slide that I gave you, which didn't have a lot of information, was very sketchy. Here it is. So the whole non-trivial part is over here. Okay, so if you read the papers, they describe, basically how does this work? Why is it called an actor critic? Because there is a critic, basically it evaluates some particular, basically if you give it a state and an action, it can sort of assign a value to the future reward of this choice. So that is the critic. So every time it sees a state and an action, it assigns some value to it. Okay, and that is the critic part. And the actor part, sorry, the critic. Sorry, I'm confusing this. The actor part is the actual, all these distributions, the policy that tells you, what is the most, what is the better probability? Where do you expect to have a higher chance of getting a better number, a better reward? That is the actual policy. This is the actor. So there's an interplay between, so both of these, there are functions there. I know I'm not describing it very explicitly, but it's complicated. And, but there are functions there that characterize this interplay of the policy and the value of states and actions. And the algorithm, so these functions are the ones that are modeled, if you want, by neural networks. I don't know if I'm answering the question, but yeah.
No, so but then if I got it right, you say that the parameters, the actual parameters of the model you're training are fixed. It's a fixed number.
Yes, it's a fixed number. Yes. So in fact, in the paper, I think we're using 2-layer networks, and we give the number of parameters that we have there. So it's completely fixed.
Okay, but technically, I mean, one could imagine that at some point you could arrive to a very, very big crossing problem where you have more parameters than, like at some point you might have to make the neural networks bigger if you really wanted to solve for 100 of deltas or something like that.
I don't think, my understanding at the moment, I'm still trying to understand it better, to be honest, but my understanding so far is that, because we're sort of using off-the-shelf things, and I'm still learning about them, but my understanding is that these networks do not have to be scaled for the learning. Now, it could be that if you use a deeper network, you get better results. And maybe if you have a larger problem, maybe you need to use a deeper networks there to get better results. So it could be that this is the case. We have not explored this. It is also people that are doing all sorts of things with these techniques. Usually, especially if you have deep networks with many layers, it's not obvious, first of all, that this thing is stable, whether you have the optimal hyperparameters. So what people usually do is they build a network with some architecture and start fiddling around with the hyperparameters to see where it's optimal. So it will also be interesting to play with these kinds of things in our case. So if we increase the number of scaling dimensions, obviously we don't want to make a very deep network because it will become slower. But it will be interesting to play with that possibility. It will also be interesting to play with the possibility other things like the norm of phi. Maybe if you give different weights to crossing equations from different parts of the cross ratio space, maybe you get better results. So that's another thing we will. It's effectively something like changing the z-sampling or doing a different Taylor expansion.
Can I ask something about the z-sampling actually?
Yes, yes, please.
So I understand you fix it and you just do the full run with some fixed z-sampling.
Exactly.
So my question says, like, have you done validation on that sampling?
Oh no, we haven't done. It's one of the points that I said that we should explore it more. So we should play more systematically with increasing the scaling dimensions, because here we just have a few examples. And
no,
also
I mean just
exactly
the points.
The z-sampling, exactly, and also change the z-sampling. We did some preliminary games where we tried different z-samplings. Sometimes a different z-sampling can have a more pronounced effect than adding 10 more operators. So it means that it's sensitive to the z-sampling and it needs to be understood better. This is definitely something to understand. Or to understand, another idea will be to, but I don't know how it will work at the end. One will be not to say take discrete points, but sort of, and instead of summing squares, like crossing equation squared plus another crossing equation squared, etc., do an integral, over a region of crossing space with some weight. The analog of the z-sampling there will be the weight, and play with that.
Well, in a way, what I would be suggesting is so instead of taking just one z-sampling sample of z points and just doing your run, you
runs.
Or multiple runs.
Yes.
What you can do, and probably it would add regularization and a lot of stability to your solutions, is you can sample at each step. Let's say you want to solve the crossing equations for all z's. So you can sample some points, do one step, choose some parameters, and then for the next step, you can change the next. Yes. In this way, you add regularization, because what you're doing is you should avoid overfitting. When you said you compare with the analytic solution, let's say the analytic solution has accuracy 10 to the -2 and your solution has accuracy 10 to the -4. But what I expect is that your solution is overfit to the points that you chose. And actually, if you change the z points, the analytic solution will still be 10 to the -2, say, because you've truncated the equations, but your solution will be overfit, and then it will be much worse. Right? So maybe because I don't see training curves, it seems that you're a bit maybe sensitive to overfitting in this by just choosing.
The number of parameters that is kind of fixed. So if there are sufficiently many points, it's hard to imagine how you would if n z is sufficiently large, it's hard to imagine how you would be able to overfit all of them.
We always want to take nz at least double of n unknowns. So in that sense, I also do not see immediately the overfitting.
The overfitting is in the neural network parameters. So your neural
network. Okay,
your neural network should have.
Okay. Yes. It's not obvious to me whether I'm overfitting there, but I should definitely think about it.
Normally I think so. Another question I have is so you use this SoftAct Critical, which is like some specific algorithm which has the property that it should maximize the entropy of the policy that it finds, right?
Exactly.
And the question would be like, this means you're trying to push towards exploration in a way.
Yes, exactly.
I don't really see why, in the sense that then you're constraining exploration by setting these windows. So it seems like your exploration and exploitation trade-off is not.
No, wait. First of all, I'm choosing these windows here for calibration reasons. In a completely unknown problem, I don't want to start with narrow windows. So I want to have as large windows as possible, and this is what I want to. I want to be prepared for that.
Yes.
So,
but even then, so my question would be like, have you tried to compare to some baseline neural network, just not a reinforcement learning, just trying to.
We haven't tried other things. There are also other algorithms of reinforcement learning, and also, as you mentioned, other approaches that are not reinforcement learning. We have not tried that. We should try, but yeah.
Yes, because a baseline would be, let's say you still have a set of equations you want to minimize.
Yes,
and
exactly.
Some error function, so you can even do stochastic gradient descent, right? And
yes,
compare
like
exactly. how much are you learning about how much your agent is learning to play and how much is just minimizing, because it seems that this reinforcement learning is supposed to help you learn some complex set of consecutive tasks. That's why you use temporal difference learning.
Right.
And in your case, it doesn't seem like in each step you choose all your parameters, all your OPE coefficients and so on. And then the next step, you sort of forget about this and choose again. And then there's not much learning to be done by the agent itself. It's not learning a strategy to play Go, let's say. It's
learning what is the best policy. So it iterates the policy every time and tries to find the best policy.
But the policy is a global policy. So it's not a global policy. It's not a very local policy in the sense that I should move in this particular subdirection. So in this sense, I would expect that it's sort of similar to some global optimization like stochastic gradient descent.
Yes.
Unless you reduce your action space and you make your actions maybe change one particular coefficient, and then there will be some strategic advantage to using like the SoftAct Critical or something like this. Otherwise, I don't see why. Well, I would like to see some comparison to this.
Yes, this is a good point. This is not we have this has come up in discussions, and again, I'm not my expertise is not in numerics, so I'm learning constantly about this. But we should definitely have a good benchmark if you want to some other stochastic gradient descent or something. I don't know, some annealing algorithm that we can compare with, where we can see that there is an advantage using this algorithm compared to that one. We should do it. I agree.
Let me stop the recording just a second. Let me stop the recording and then we can proceed with the discussion, but just so that we have a smooth finish to the video.
Yeah, and just one last thing, like, do you have some